Good afternoon, everybody. This is Trevor May, VRF and duct-free split technical specialist with Standard Air and Lite, here with a tech tip, part of our little mini series here covering basic ductless operation. We'll get into some troubleshooting fundamentals, but most importantly today, this little mini series is going to be focused on just the basics of ductless operation. This is just going to be the basic fundamental on how we look at a ductless system, how we understand the ductless system, and more importantly, starting to build the foundation in order to successfully troubleshoot a ductless system. And of course, that starts with understanding the operation. So that's what we're going to be covering today. So let's get into it. So the basics or the basic operation of ductless equipment. So no matter whether we're dealing with a single zone or a multi-zone, or whether we're dealing with 208, 230, or 115 volt single phase only power, we're going to have that power coming into the outdoor unit to run the machine. From there, we're going to take that power, we're going to take that AC incoming voltage, and it is going to enter into the main PCB board, or the main board in the outdoor unit. Now, these boards will differ depending on what kind of unit that you have. There are some, such as the multi-zones, where we have a split type board, where we have a main PCB and an inverter drive. And on the single zones, depending on the tonnage, we just have one integral board that actually is an inverter drive and a main PCB board in one. But nonetheless, we have that AC power that comes in and powers that board. Now, inside of that ductless unit, we're going to be using AC and DC power. That DC power is derived by taking the AC voltage and running it through what we call a rectifier, or rectifying AC voltage to DC voltage. And that is achieved by using a diode. A diode essentially is like an electrical check valve. That electrical check valve allows voltage to pass through, but not back, achieving the AC to DC conversion. Now, in ductless systems, we use AC and DC voltage, as we're all aware now. AC voltage for things such as crankcase and base pan heaters, DC voltage for things such as compressor, outdoor fan motor, and reference signals from thermistors to be able to tell the unit what it needs to do. Now from there, we take that AC power, we rectify it over into DC, and we send the AC and the DC voltage out to the appropriate places depending on what time of year it is, how the system's running. But as a generic overview, we're going to go ahead and send that out to different parts of the system. Now, in this case, we're going to carry on and look at the compressor, the actual inverter compressor operation. So that AC power, we now know, enters into the main PC board. That AC power then enters into what we call a bridge rectifier, as I covered earlier, which takes the AC voltage over into DC voltage, or we get that rectification process. Once we rectify the AC over into DC, we need to run that through what we call a reactor or an inductor. Whatever you're familiar with the term, technically both of them are right. I personally prefer an inductor, but either one of them, as far as terminology is concerned, is correct. So essentially what the reactor or that inductor is it a choke on the line itself. So what it's doing is it's cleaning up the DC sine wave, or that newly generated DC power. Now, the reason that we do this is because we have an inverter-based operation. The name of the game, whether you're dealing with a ductless system or whether you're dealing with a larger commercial VRF system, is smooth, clean, consistent power. Okay, so that's why we're filtering not only on the DC side, but we also filter on the AC side to clean up the incoming power, and then more importantly, to clean up that newly generated DC voltage. Okay, so once we've taken that AC power, we've rectified it over into DC voltage, and now we've taken that DC voltage and ran it through what we call our reactor or our inductor to clean it up. We're now going to enter into the IGBT, which stands for an insulated gate bipolar transistor switch. It's essentially a fancy name for a switch that pulses DC voltage to three common terminals. Those three common terminals are listed as U, V, and W. And the really nice part about those three common terminals, it's that is used across the board, whether you're dealing with a Mitsubishi system, whether you're dealing with a Daikin system, or whether you're dealing with a Carrier ductless system. Those three terminals will stay the same across the board, and they also will be appropriate for the fan motor, as well as some of the models do use a U, V, and W for our outdoor fan motor, since we're working under that same pulsation of DC voltage. Okay, so let's kind of just recap of what we have so far. So we have our power in, we have our AC power that enters into that inverter drive and main PCB, depending on what type you have, whether you have a split type board or a single board. We take that AC power, we run it through our bridge rectifier and convert that over in DC voltage. That DC voltage is filtered through that inductor or reactor. And then we take that DC voltage and enter it into our IGBTs, or those pulsating switches that pulse to those three common terminals, U, V, and W, which are the legs that go directly to your compressor. Okay, now what we're going to look at that as is a simulated AC voltage. Okay, now when we say simulated on there, a lot of guys will ask, what does that mean when you say simulated AC? What we're doing is we're essentially mimicking an AC sine wave by pulsing DC voltage to the compressor. So if you want to look at it from a basic overview, we're essentially fooling the compressor through a sine wave. Since the compressor doesn't really know the difference between AC or DC voltage, what it does know is the sine wave. And by pulsing DC voltage, we can mimic an AC sine wave, which in turn can control our speed of the compressor. Now, the biggest difference between a inverter compressor and a non-inverter or a stage compressor, whether you have two stages or a single stage, is going to be the fact that we have that nice slow start with these inverter compressors. So if you think back to the HVAC basics or your fundamentals, you think of a fixed speed compressor and you have a contactor, whether it's single stage or two stage. If it's a two-stage piece of equipment, you have your first stage, which compressor one gets the call, pulls in, and runs. And typically, the most amount of current seen is going to be on that initial start when we power that compressor. That's going to be the peak amount of amperage or the amount of power or the amount of money that you're paying to run the equipment. However, when we go into the inverter-based operation, because we have that slow start and we don't have that initial inrush current, we're drawing less power, in turn, saving more money. Okay, now when we talk about the simulated, we talk about pulsing. The pulsing creates the simulation to simulate an AC sine wave. You'll often see this referred to as pulse width modulation, and I'll explain that here in a few minutes on what that term actually means in reference to what we're going to be looking at as technicians to try to troubleshoot and understand that a little bit better. So if we look at this from a schematic point of view, you'll see here you have your main power coming in. Now, in this case, of course, we only have single phase equipment in the ductless product line, so we can just knock off this phase right here for line 3. We have our incoming power, as you can see right here, which is entering in to this little diamond looking shape. This is the bridge rectifier, and you can see here by the electrical layout on here, you have your diode stacks. And this is where we talked about before, where that AC to DC conversion happens. So AC power comes in, enters in through one side of the diode on there. Remember, they act like electrical check valves. So they're going to allow voltage to pass through, but not come back. Okay, and that's where we generate that DC voltage at. From there, on the outlet, we now created the DC voltage. So we have a positive and a negative bus. Okay, we continue along this wiring or this piping diagram, or this layout or the schematic. And now what we have is an inductor. We talked about the inductor before, where that's going to be to filter the newly generated DC voltage. Okay, so this is filtering the DC voltage, and then next we run it through a capacitor bus. Now, capacitors by nature store and release charge. This is in an effort of when that sine wave reaches its peak, these capacitors are going to absorb that charge. And when that sine wave reaches the very pit or the bottom of its wave, they're going to discharge. Now that works in an effort to keep that sine wave as smooth, clean as possible. Essentially, we're trying to keep it perfectly straight. While it'll never achieve that, it is going to work in unison with the inductor or the reactor to try to keep a smooth, clean, consistent sine wave. In this case, we're looking at a DC sine wave or power that's feeding into our next part that we're going to look at right now. Now, if you come over past the capacitor buses, we have these little switches on here, and you'll see that they feed to 3 common terminals. These 3 terminals are your U, V, and W terminals. Okay. Now you'll have a positive side or a positive bus. You'll have a negative side and a negative bus. These switches are those IGBTs, or those pulsating switches. Okay, so what happens is in the board itself, there is an algorithm or a set of rules that is pre-programmed from the factory. Now that program looks at the sensor information that's being fed back to that main PCB board, excuse me, to pulsate voltage to these three common terminals, W, V, and U. Now, depending on our deviation from set point, depending on the compressor speed, depending on EXV position, it will pulse voltage to three common terminals, which we talked about as being W, V, and U. And that goes directly to our compressor, which in turn controls the speed. So when we talk about those IGBTs, this is what we're actually looking at from an electrical point of view. Switches that open or close on a positive or negative DC bus that simulate an AC sine wave. So here's the trick question, and where everybody kind of gets goofed up with this. Are these inverter compressors AC voltage or DC voltage? Okay, most of you would probably answer and say DC, because a lot of you see the DC on the side of the compressor. And that's not correct. What those compressors are with that DC marking on them is digitally commutated, not direct current. Those are actually AC compressors. So what we're doing is, remember, we're simulating an AC sine wave. Okay, so that compressor is AC. We're trying to fool it with DC voltage so that we can control its speed to a much finer degree. So we're pulsating voltage on a positive and on a negative bus directly to a W, V, and U to simulate an AC sine wave and have a much finer control of that power, so that in turn we can control different percentages of speed, 20%, 40%, 60%, and so on. Okay, so these compressors are AC compressors. However, when we are troubleshooting and taking our meter and going across the W, V, and U terminals, we are sending DC voltage, true DC voltage to the compressor, but we're pulsing it to simulate the speed and to simulate an AC sine wave. Okay, so let's back that up. Compressor is an AC compressor. We are sending DC voltage to it. Okay, so if we look at that pulsing as a square waveform, and essentially that's what we need to look at it as, depending on what incremental pulse that we're going to get out of those switches that we just covered, the IGBTs. Now, as you can see here, this isn't the only thing or the only amount of pulse that is limited to that IGBT. It can pulse anywhere between here, but as a representation, we can look at a square waveform as a 20% pulse, 40% pulse, and 80% pulse. Now, what happens here is you have a pulse on the positive side and you have a pulse on the negative side. And that's where we get a pulse on the positive. We come down and get a pulse on the negative, and we start simulating the AC sine wave. And this is where that simulation of that pulse width modulation occurs. Now, when you hear the term pulse width modulation, which has become popular with many household appliances, air conditioners, just because of the energy efficiency that's associated with it, what that term actually means is the pulse, which would be the amount of signal sent to the individual terminal, whether it be W, V, or U. The width, in this case, would reference this chart, or the amount of pulse that's actually being sent, whether it's a 20% pulse, a 40% pulse, an 80% pulse, or full modulation. Okay, and then of course the modulation would be the frequency that the algorithm is going to pulse that off onto the switches to control the speed of the compressor. Now again, that's based on pretty much every sensor that feeds back to that outdoor board, including the sensors on the indoor unit and positioning of different valves, compressor speed. So everything that system really is reporting back to the board, the compressor is looking at to try to get to a speed that's going to make the most sense and be the most energy efficient while being able to meet the requirements of the customer who's trying to either heat or cool their space. Okay, now we look at basic makeup of a ductless system. So we talked about the inverter operation process as far as the compressor speed, as far as how we pulsate DC voltage on those IGBTs and the different boards, and how everything really flows with the outdoor unit. But now we need to look at how the information is being given to that controller, or if you want to think of it as the brains of the operation, which would be the main board. So as a rule of thumb on the indoor unit, whether you're dealing with a cassette unit, a high wall unit, a ducted unit, a floor console, all true ductless indoor units on the indoor unit have two main sensors. First one is going to be your T1 sensor, which is your return air temperature sensor, or in this case, your indoor room temperature sensing thermistor. You have your T2, which is your indoor coil temperature thermistor. Okay, that's going to be controlled for things such as the anti-cold air function, where in the heating mode, when we have the first initial call for heat, you'll notice that the fan doesn't run. And what it's doing is it's looking at the T2 sensor or the coil sensor to figure out when that coil is warm enough to turn the fan on so that we're not blowing unwanted cool air on our customers. Just to cite an example of one of the many operations that that sensor does go into play with. Now we look at the multi-zones, you'll notice there's a T2B. Now what this is an outlet temperature sensor of the EXV. The EXV is on the outlet side, and we'll just use the cooling mode as an example. We need to figure out what temperature after we create that pressure drop or that change of state from liquid refrigerant to a mixed phase refrigerant. We need to monitor that temperature to make sure that that valve is set in the correct position. And this is what this T2B sensor looks at. Now on the multi-zones, you're going to have one for port A, port B, port C, etc., depending on how many ports you're actively using. Okay, so for indoor units, that's really going to be your basics. And I kind of dived over with the T2B sensor because that's really more so in the outdoor unit, but it does have relevance as far as how the indoor units are being fed refrigerant. Okay, but as a rule of thumb, T1 and T2, which is a return air temperature sensor, and a coil temperature sensor are going to be your two main sensors that make up any ductless indoor unit. Now let's move on to the outdoor unit. The outdoor unit is going to have three main sensors. You're going to have a outdoor coil temperature sensor, an outdoor ambient temperature sensor, and a compressor discharge temperature sensor. Of course, the compressor discharge is protecting the compressor from an overheating situation. The outdoor ambient and the outdoor coil control things such as fan speed and, most importantly, defrost. Okay, but those are going to be the three main sensors that make up our outdoor unit. Now we look at our TS on there, which is the setting by the remote controller. That could be a wired remote controller or a wireless remote controller. So the setting temperature by the customer is going to ultimately play into how the system needs to figure out where it needs to run at. Now, all of that feeds into our TD, which is the target temperature controlled by that microprocessor. You look at that and go, whoa, what does that mean? All that means is it's taking in all this information from the indoor and from the outdoor unit and figuring out, we'll call it a sweet spot of where it needs to be at and where it needs to run and how it needs to change as the system starts running and getting the temperature close to the set point. So it's looking at all this information and making logical decisions. It works exactly the same way as our brains do. Think of information in the environment being fed back to us. Once we have that information, we process it and then make a logical decision based off of that. The ductless system is doing the same exact thing, except it's using thermistors to report the information back to the main PCB or the brains of the operation. And then from there, the algorithm or the set of rules then makes a logical decision based on what information that it's given. Okay, now there are three correction factors you'll see below. You have your delta T1, T2, and T3. These aren't the only correction factors, but these are going to be the most common that we come across. So the first one is going to be your correction by turbo mode. Turbo mode is a feature that is on the wireless remote controller. Now, when you initiate this feature, the turbo mode is essentially looking at the sensible load in the space, not the latent. Ductless systems by nature are sensible load carriers. They really don't focus too much on the latent load depending on which model you have. Now, our high tier model does have a relative humidity sensor built in, but that's not on every single indoor unit that we offer. That is only on the high tier high wall units, which is the 40 mph. Okay, but this correction by turbo mode essentially is going to rev everything up into high speed. So that's your indoor fan, your outdoor fan, and your compressor. The rules of this turbo mode are when it is hit, you'll see on a unit that has a digital screen or a readout, you'll see on there to indicate to you as a visual indicator that this mode is active. If you do not have a digital display, all you're going to hear to confirm that this is in turbo mode is an audible beep. When it runs in turbo mode, it has 30 minutes to try to get to the set point that you have for turbo mode. Now, when you hit turbo mode on there and then you pick, let's just say 65, it has 30 minutes to get that space to 65 degrees, and it's going to run at full modulation to do so. Essentially, it's trying to get to set point as quickly as possible. That is what our turbo mode is capable of and what the main purpose of the turbo mode is. Now we look at our Delta T2, which is a correction by follow me. This is an extremely popular option and one that I get questions on all the time. So on the wireless handheld remote controllers, they have a follow me button on there. And when you hit it, instead of taking temperature at our T1 sensor, so if we look back at that T1 up here, indoor room temperature sensor, that is the default sensing location for all ductless equipment. Okay, when we hit the follow me function, we are now saying, system, I'm not looking at T1 anymore. I'm looking at this remote controller. And it communicates to that particular indoor unit based off of an infrared signal. So the most important thing that I can tell you about follow me is when a customer wants to do this or they have questions about it, if they are going to use the follow me mode, they need to make sure that that is the only wireless control that they are using for that indoor unit. You cannot control multiple indoor units from one wireless controller when you have the follow me enabled, because it's locked into that particular unit to read the room temperature, report it to the unit so that it can run properly and maintain temperature. Okay. The other biggest thing with follow me is you don't want to put this system in follow me on the wireless remote control and have the customer put the remote that's not in line of sight of the indoor unit. If they decide to put it in follow me and then put it in their dresser drawer, or one of the kids take it and they end up losing it, it will drop out of the follow me function. And as a default, it will look at the T1 sensor, because the system has to realize what the temperature is in the room in order to be able to control and modulate the rest of the system properly. And then finally, our Delta T3, which is a correction by temperature compensation in heating mode. So what this is you can essentially put an offset on the return air thermistor, depending on if you're overheating or if you're underheating a space, and follow me just hasn't been a reliable option to resolve that. Okay, now essentially what it's doing is it's telling the T1 sensor, hey, I'm reading 75, and you program a custom offset on there to read 4 degrees less than what the actual reading of that temperature sensor is. So if it's reading 75 and you put a negative 4 degree offset on there, that system is going to read 71 at that return air sensor. And the reason that we do this is, of course, if you have an overheating situation, we're essentially fine tuning that sensor to meet the needs of the customer to make sure that they're satisfied. So as a general rule, if we take just a generalized overview of what we've talked about so far, we have a basic makeup of a ductless system. We have an outdoor PCB and an indoor PCB. We have our T1 and T2 sensors, which we know as return air, and indoor coil temperature sensor. We also have our TS, which is the set point by the controller, whether that be wired or wireless. We have our fan speed, which reports back to the indoor PCB, and that's looked through as RPM, or revolutions per minute, just like we would look at in a car with an RPM or a tach meter. The board inside of there has logic that registers when that fan speed is too low or too high. But more importantly, during normal operation, it needs to know how fast that fan speed is running and whether it needs to increase or decrease based on a user set point, or if the fan's in auto mode, based on a particular temperature on that indoor coil. Okay, from there, we have that information that's fed over into the indoor board, and in turn, we get control for the indoor fan motor for different speed settings. And if your unit is capable of having a swing feature with the louver, it will receive a command from the wireless remote controller, and then in turn, execute that command and either swing that motor or adjust that louver's position, again, if your unit has one. Now we look at the communication between the indoor and the outdoor boards, because they have to talk for this system to work properly. Communication is carried between the L2 and the S wires on a 208, 230 volt system. On a 115 volt system, that communication is carried between neutral and the signal wire. Okay. And that's how they talk between indoor and outdoor. Now, I could go in and start to tell you the troubleshooting processes, but I really think that's diving a little bit too deep for this particular class. So for right now, we're just going to understand where it's carried between. And in later classes, we'll cover how to troubleshoot what's good and what's bad. Now, in your outdoor unit, you have your three main sensors. We know those as the outdoor coil, outdoor air, and compressor discharge, which is T3, T4, and T5 sensors. Okay, that information is fed into the outdoor board, and through the communication line on the signal wire, the information for return air, coil temperature, and the setting by the remote controller is transferred to that outdoor board. So the outdoor board, or the brains of the operation, knows what's going on with its indoor or indoor units, depending on what type of system that you have. Okay. In turn, it's going to make logical decisions such as changing the positions of the EXV or the EEV or the expansion valve, changes to your compressor speed, changes to your outdoor fan motor, and then also changes to your four-way valve, of course, depending on which mode you're in, whether that be heating, cooling, or if the system is off. So that's it for today's Tech Talk. I hope you guys enjoy this. I hope you took something from it. Of course, we still have our normal training classes that we conduct in person and also online, especially amidst the whole COVID-19 pandemic situation. But the same classes are still being offered. We still offer our full 4-hour classes, which go over ductless and VRF generalized overviews, and then also get into the installation, the service, and the troubleshooting. And then we have specific workshops that are 2-hour screenshots in the morning from 7 a.m. until 9 a.m. that focus on particular parts or particular phases in a VRF or ductless system, such as installation, troubleshooting, product overview, and application. So all of these classes will still be available in 2021, of course, depending on how the COVID situation plays out. But we have plenty of classes that we offer not only online, but in person to keep you guys up to date with all the recent product changes and to make sure that you have a good fundamental understanding on how to troubleshoot, apply, and install VRF and ductless systems. And of course, if you do not have my contact information, you can see on the screen here, I have my number, my direct extension, and also my email. Product manager information for the ductless product line and the VRF product line are listed below in case you need to contact a product manager. And the biggest thing that I want to point out on here is that for some odd reason, if I'm on vacation or I'm just unavailable because I'm just backed up with calls, I'm just your first point of contact, not your only. If for some odd reason you can't get a hold of me or you left me a voicemail and I can't get back to you, within half an hour or 15 minutes or whatever the situation may be, you're always more than welcome to call into our service department and dial the following extensions of these three gentlemen. John Homan is the service manager, followed and backed up by Bob Freed and Lee Peterman. And of course, their extensions are to the right of their name. I appreciate you guys taking the time out of your day. Hopefully you learned something out of this. Hopefully you've taken some of the things that we've covered and start to build a foundation for starting to work with ductless systems. And we'll see you next time.